limitation of antioxidant migration in polypropylene food contact films using clay nanofillers. In this work, in these 10 minutes, I'll outline the problem, describe our methodology, present the key findings, and finally discuss their implications. The role of plastic food packaging is to protect, preserve, and to transport the packaged food. Generally, this packaging is no more than film. This film is made up of polymer matrix and additives. As a result, these additives tend to migrate into the food they come into contact. This migration raises regularity issues and potential health risks. Nanofillers offer a potential strategy for limiting this migration while preserving the material's performance. Depending on the type of the polymer, polypropylene accounts for 26% of plastic demand in Europe. It is one of the most widely used polymers in the packaging sector, thanks to its technical properties and low cost. For this why we choose this polypropylene as our main matrix. Polypropylene is a semi-crystalline thermoplastic belonging to the polyolefin families category. It is produced by polymerization of propylene monomer. It is used generally in automotive industry, electricity and electronics, flooring, toys, and packaging. There are various types of packaging: plastic, metal, wood, paper, glass, but the plastic packaging is the most commonly used due to its lightweight, strength, and low cost. The packaging industry consumes approximately 39% of all plastic used in the world. It is used generally in butter packaging, dry goods packaging, plastic bags, syrup bottles, egg packaging, yogurt pots, and bloods. The interaction between the container and the content. Here we have three types of interactions. The first one is the absorption. Here the plastic absorbs certain molecules from the content. The second one is the permeation, which is the passage of the gas, such as oxygen, through the packaging. The third one is the migration, which is transfer of substances from the plastic to the content. The potential migration of these additives, which are often toxic, can have serious consequences for human health. This risk is particularly high when polymers are in direct contact with food, particularly fatty food, since the PP is a lipophilic substance. The incorporation of nanofillers into a polymer matrix has been demonstrated to enhance the material's barrier properties. The nanoparticles have been demonstrated to generate a tortuous maze-like path, which has been shown to significantly impede the diffusion of gases and vapors. This is, in turn, has been demonstrated to engender a marked improvement in resistance to permeation, migration, or diffusion of molecules. The aim of this study is to assess the effectiveness of incorporating nanofillers in reducing the antioxidant migration in polypropylene films intended for food contact by evaluating the migration of the erganox, which is a stabilizer, through the PP films to a fat simulant, which is ethanol 95%. Secondly, by studying the influence of physicochemical parameters such as temperature and time on the migration rate. Third, by studying the effect of adding 1% of cloisate 50A on the limitation of erganox migration. For this while, we used three materials. The first one, which is the polypropylene. Second one, which is a stabilizer, which is erganox 1076. And finally, organomodified nanofiller, which is cloisate 15A. These tables list different material prepared. First one is the net PP. The second one is polypropylene with 1% of stabilizer. The third one, which is polypropylene with 1% of stabilizer and 1% by weight of nanofiller. All the materials were prepared in twin screw extruder. After preparation of the film, the materials, the films of this material are prepared by compression and hydraulic press. The average thickness of these films was about 140 micrometer. Migration study. This migration, each film was introduced in a tube test with 20 milliliters of ethanol at 95%. The sealed tube was introduced in an oven at different conditions of temperature and time. After the required time, each film was analyzed by infrared spectroscopy. The result. Calibration curve, the concentration of erganox in each film can be quantitatively observed by following the specific band absorbance of the stabilizer, which is 7032 wave numbers. The quantification of the erganox scattering in the PP matrix requires the use of different diffusional model by resolving the fixed second law. Here we have these graphs illustrate the dependency of the loss, theoretical and experimental loss of mass versus the time. Here we can see that the loss of mass increases gradually with increasing time. A significant increasing of the loss of mass is observed at high temperature. Same results are observed for the material to which we added 1% of nanofiller. From this result, we deduced the diffusion coefficient and the half migration time through the PP film and the PP film with nanofiller. Here we can see that the diffusion coefficient increases by increasing temperature, but the half time is decreases when adding with temperature. Adding 1% of nanofiller, we observed a reduction of the diffusion coefficient, but while the half-time migration has increased. To conclude, the study highlighted the migration of erganox through PP film in contact with a fatty stimulant. The results show that migration is highly dependent on experimental parameters like temperature and contact time. It is therefore essential to optimize material formulation and control usage parameters to ensure food safety. The result revealed that the incorporation of 1% of nanofiller decreased diffusion coefficient by 25% compared to the virgin polypropylene and increased the half migration time by 44%, indicating that the introduction of colloidate into the polymer matrix slows down the migration of the erganox. This may be explained by the barrier nature of the clay sheet dispersed in the polypropylene matrix, which create a more tortuous path for migrating molecules. For industry, this offers a pathway to meet stringent regularity standards and develop next generation high-performance films. Looking ahead, we believe this clay nanofiller strategy could be vital for enabling the safe use of plastic in food contact. Our future work will focus on scaling up this process and testing its efficacy with a wider range of additives and food stimulants. I'd like to thank you for your attention.